Good morning, everyone, and welcome to the second session of the Ocean Observational Pyramid. My name is Richard Hall. I'm Equinor's specialist in remote sensing technology. I also have a deep connection to Tromsø, having lived here for 9 years. I work for the Norwegian Polar Institute and Kongsberg Satellite Services. But most importantly, 2 of my daughters were born here. So it's very good to see that this year is Tromsø's Year of the Youth. So, one thing we forgot to mention in the first session, you can ask questions online. If you ask a question, it will go to Paula, and she will tell me, and I will raise it for you. If we have time. But if we'll try and keep to the time table as much as possible, and that will leave for questions at the end of the session. So if we don't get time during the speech, don't worry, we'll take it at the end. Does everyone understand? Do the presenters know that I'm a strict timekeeper? Now you do. So, to start, we have Ulf from Ulf Jonsel from the Swedish Polar Research Secretariat, giving the keynote presentation on Polar Connect, an Arctic observing system through fiber optics. Ulf, the floor is yours.
Yes, thank you very much. The speaker is on, yes, good. Thank you so much. Thank you, the organizer. Thank you, audience, for being here. I will talk about Polar Connect and the observing and science opportunities within it. It will be an overview presentation. And I will like to first say here, Julia Muchowski, who has done a lot of this work. My part of this project and the project team is more on the environmental side, keeping the environmental group together on the environmental permitting, environmental assessments on this. So this, on the technical aspects, it will be a layman's perspective of this, and some will appreciate it, some will not appreciate it, but that's what it is. So you see, what is Polar Connect? Yes, Polar Connect, you can see to the left, is an artistic review here of a fiber optic cable through the Arctic. So everything here is, nothing is settled on the route or the landing station. It just gives you an impression of what we are trying to do within this project. And the sensing and science opportunities, what are those? If we take it from the core benefits and kind of zooming out here, yes, it can then contribute to science and environmental monitoring of the Arctic Ocean. That's kind of the core values we're working on here. It will then, of course, bring a new broadband connection to the people living in and also acting in the Arctic. So it gives better broadband, you could say. It will, of course, not only be able to monitor the environmental aspects, but also human activities in the Arctic, as was touched upon also here in the previous session. But when we now here also zooming out, it will also enable data transfer for any scientific collaboration with this digital highway. And as you probably understand, the main driver is to have a fiber optic connection between EU and the Indo-Pacific region. So it will be kind of the highway of internet. It will be complementary to the routes today to this region from Europe, which mainly goes through the Red Sea. It then provides also a digital resilience, and it is the shortest possible path to this region. And that could be shown like this. Now we are here in an Arctic setting, so most of you are probably fully aware of this. But, well, you know, did that go away? Yes. So, you know, it's about the how we project the maps. You can see 3 routes via United States, via the Red Sea, and Polar Connect. And with this projection, it does not look like this will be the shortest, but as you see, we are on the globe, and it will be absolutely shortest path, which then guarantees the reduced latency and improves connectivity. So, getting in a little bit about the project before getting also to the more in detail on the sensors is that all telecommunication is in fiber optic cables. The most of it. The first leg, you can talk about satellites, but the first leg, that's only the first leg. And then you come to these fiber optic cables, and between the continents, the subsea cables are kind of the highways. And they have a lifespan of about 25 to 30 years. So many of them are already getting old. And you can see there are a lot of them between the EU and the United States, then put there by private companies. But why is there then no cable yet in the Arctic? That is the difficult question to answer here. And, well, basically saying it's putting up something almost as white as this, it's the sea ice. So, I mean, the sea ice here is, of course, a challenge to lay a cable, and that is what we're now doing in this project. We're making it a feasibility study to see that this is technically feasible. And this does not start from scratch. We have been mapping, as you may know, the Arctic basin for with a lot of intensity for the 20, 30 last years. And here I show what was been done with the ship that my organization is using, mainly Oden, and then you see also in black all other routes. So, I mean, we say nowadays that we have mapped about 25%, a third of it is mapped by Oden. So this is, of course, extremely important data that we have now collected for making it to see where can we put this cable? What is the route of this cable? We need this data. And we need more detailed surveys. So that's what we're also doing in the project. But secondly, the ice management. That is also something, a lot of experience that we have then gathered with all the Arctic expeditions that we have done with Oden, and ice navigation, ice management. This is a kind of a parallel project which was drilling into the Arctic, and you needed this kind of ice management where you have actually 3 ships, one kind of scouting, making it to smaller pieces, and then a ship before this drilling vessel that made even better conditions than for the cable laying vessel. And then you would imagine here, hey, but this is you're drilling on a one spot, but you need to recall then that the ice is moving. So it's kind of similar to laying a cable. The same kind of operation is here needed. And this was done, this is done from the drilling in 2004, and we had a similar project in 2022. Everything was planned for making this kind of drilling and ice management, but it was then due to the relations with Russia, we could not continue the operational planning. So this also is maybe why my organization also is behind this. It's not only the science opportunities of the cable itself, but this also calls for a new Swedish icebreaker that is now on the Swedish government's table to hopefully take a positive decision about. And it's for the cable laying operations, for the maintenance, but it's of course for science. So this is part of this project. We need the Swedish icebreaker. Something about the funding. I mean, you can see the funding numbers and who has put support to this. And this is by saying we don't have the funding for manufacturing the cable and all the sensors I'm going to talk about, but this is the feasibility study. We have shown in reports that this is possible to do. And what is also in the project then is to then have the setup of the so-called the special purpose vehicle for this, so where we actually get also the commercial funding into this, because it's not only about sending scientific data, as you understand. I mean, it's about cat pictures and, of course, the financial markets who likes the short latency. So, And this is mainly now Nordic. We have many of the Nordic educational and research operators network in this, but also the European counterpart within the project. So about sensing opportunities, if we're getting there, and this will just be an overview then, not going into the full technical details of it. You can use the cable itself. You can use sensors, more maybe traditional sensors that you attach to the cable. And the opportunity and the benefit here is that you get then continuous streams of data. And we can also use the cable for supporting other systems, which more measures along the water column. So this is in the opportunities. So the first in itself, and many of you might know this much better than me, but it's the distributed acoustic sensing, DAS, which is basically you put a laser pulse into the fiber optic cable. If you have some disturbances in the environment, you can track that from the Rayleigh scattering of the signal. So it's a phase shift in it, and you can do incredible things with this. And you can read a lot more about DAS, and there are similar techniques more on temperature. But this is the basic of it. And some few examples in the literature, and you can find a lot more. Instead of using classical seismometers and that kind of networks, you can use this cable, and this is just to show more or less that the seismometer to the left and the DAS application to the right, and you get a similar result. So it's and also you can do with the DAS, you can use on much higher spatial frequency. This is when I started with this, I think I was stunned by this, that you can track whales from this. You can track the sounds of whales. With the changing Arctic, we need to survey if there are disturbances, if there are differences in the whales' behavior. You can then track them and by these here in an application with 2 fiber optic cables. Fantastic, I must say. And this is more of looking at the temperature. The DAS is, as I understand it, more of the changes in temperature. It's best to detect the changes or sudden changes, but you can also use this then as shown here, also 2 parallels with a more classical thermometer to end the DAS example. So you can say that, well, this can bring you insights into the ocean and upwelling and those parameters in oceanography. And then if going to the smart sensors, as they are called, science monitoring and reliable telecommunication. Those are more of the classical sensors. There are 4 sensors that are mainly used on these. These you put at the distances on the cable that you would like. Here, of course, there is, as I understand, a lot of development on what other kind of sensor would you put there. As I understand from the oceanographic community, salinity would be a very interesting sensor to put here, but it has its challenges. So, and you should also remember that these should be here for 25 to 30 years. We would like sensors to have that longevity. Good. And so this is just summing up. We can do a lot of this in different scientific fields: oceanography, climate, geophysics, and marine biology. So I'm not taking up everything here, but you can read in the literature that there are these opportunities, and we in the project are always interested in what your ideas or input to the project would be. So that's where we are. And then, just to show this, if you have played this game or puzzle Spot the 5 Mistakes, you can play that with this picture, but it's just to give you an impression of it. Finn fem fel for the Norwegian audience. But anyway, it's saying that those kind of observatories that was also presented here before, the HIOS of the EU funded and the Canadian Neptune, for instance, well, you could use then the fiber optic cable, of course, to send the data back home. So this makes a very nice match. And I should say that our project, the Polar Connect, is not doing the full observatory. Those, we have other initiatives, but of course we can work together, and we are working together. Well, as I said, we're very interested and have been very interested in the scientific community's input. We have had several seminars on this topic, and you can see that the main interest for where we should put these kind of sensors and where we should collect data is in the deep ocean. And the deep ocean is more or less here, and that means also that we are in international waters, which of course is a benefit for us concerning data collection and data management. And then sensor development, as I talked a little bit about, we are in the project also talking with institutes, universities, and the leading manufacturers of sensors to put what could we put on this cable. Not only for the Arctic, of course, they could be employed wherever there is a cable. So that is also part of Polar Connect, and there's also this thoughts or ideas, initiatives on kind of more plug and play, that you put here a socket on the cable, and then you can come back and, I plug this in now with this specific instrument. That's, I think, also a really interesting avenue for doing further work. Yes, and then data policy and data management in this. And I was using this picture here to see what we are aiming for. I mean, on this part of the project, it is to have a better understanding of the Arctic environment. And for that, this, with the DAS sensing, the smart sensing, everything can contribute, not least, as I said, with the continuous measurements. I mean, the cable is all the time there. So, but we, of course, understand that there will be a lot of other data that can be collected on human activities. So this calls for a data policy and data management that is taken or that is formulated in dialogue with international stakeholders. Since we are in international waters, any country that would like to put sensors or using this cable for their exclusive economical zone, of course, that could also be considered, but also for the international waters. There is a work here, of course, to have the data policy, to work with trusted data centers, perhaps disciplinary centers that have a certain level of standard, and then to separate, if necessary, what could be called as sensitive data to what could be open scientific data. Under the as we say when talking about fair data, as open as possible, but as restricted as necessary. So that is necessary to, as we see in this project, to really get the data for understanding the Arctic better. And as a last picture, I show this again. I hope that I have shown that we can here contribute to science and environmental monitoring with this project. I cannot, as this is not a presentation of any results from the data, this is a presentation of the project and the opportunities we see with Polar Connect from the scientific and sensoring side of it. So I think I stop there. Thank you very much.
Thank you very much, Ulf. We do have 2 minutes for questions. Quick questions? Please introduce yourself.
Yes, thank you. Tom Mulesman from Time Magazine in the United States. Presumably, the sensors on the cable could be used to monitor traffic of submarines in the Arctic Ocean, so it introduces a sort of security question here, and how might the Russians respond to this, or other countries? What thought have you been giving to that
yes,
question?
no, of course, and that's why I'm mentioning this, that we of course understand that there could be sensitive data in this, And the project is considering this, having dialogue, but just exactly those dialogues are kind of outside the remits of my part of the project, but they are considered. And I mean, it's all like, I mean, it's not only in the Arctic we have those cables, we have them, as you saw on the map, so it's also a kind of a general question how to separate the data so we can have open scientific data as well. And I think there are good examples you can work and elaborate on. So, yeah.
One more question?
Just a quick comment. I've been at the Smart Cable meetings with Bruce Howe a number of times, and one of the things, of course, he's limited by what his funders want for the seismometers and temperature. But one of the other things that the whole group, including the other fiber optic cable companies, wanted was hydrophones. So that was the #1 priority, and that's a relatively simple technology that even the companies wanted on there.
Thanks.
Thank you very much. Just a quick Tromsø question. Where will landfall be in Europe?
Yeah, it's not decided, but it's, I mean, the idea is to have it in the northern part of Scandinavia. Yeah, so we cannot say exactly where at this point. Yeah. None of those, I mean, those are, as I said, the artistic view of this, but then of course it's goes to the dialogue with the different nations and stakeholders. So, yeah.
But at the landfall site, you will need data processing, data storage, and energy to...
Yes, exactly. Yeah, that's what we need, the so-called landing stations, yes. So that is needed, so there needs to be a kind of an infrastructure there already. Yeah.
So, thank you very much.
Thank you very much.
A round of applause. And now I'd like to introduce our next speaker is Philip McGillivray from the US Coast Guard. I won't say much, but I just say he's actually celebrating a very significant anniversary this year. But I'll let him, he can tell you as much as he wants to tell you. Thank you very much.
Okay, let's see. So I'm not speaking, although I've worked as a science liaison for the Coast Guard for 28 years, I'm not speaking for the Coast Guard today. I'm speaking as a dual employee of the Office of Naval Research's International Collaborative Engagement Program for Polar Research. And so I wanted to talk today about some of the technologies that we've discussed, and this is part of the remit for this meeting. Satellite sensors, new sensor technologies, remote sensing coupled with in situ observations, dual-use technologies for science and security, and next-generation observations, what's coming in the future, including with unmanned systems, and how do we get the data back from those systems, and how do we sustain this over the long term and ensure interoperability. So starting with satellite systems, I just wanted to point out that we're at the peak, or coming down a little bit off the peak of space weather right now, and that's an issue for communications. So this is an overview of what's going on. The most important thing for satellites for me, as terms of sea ice, is the NISAR satellite, which is a NASA Indian satellite. It's synthetic aperture radar, so it can see through the clouds. It has a reasonable refresh rate, depending upon what latitude you're at, and it has pretty high resolution, especially useful when combined with other data. So in terms of space weather, we still have this, in a way, solar telescope that's providing really high resolution pictures of what's going on the sun. There's another new satellites, the tracer satellites that have been up. They're at Lagrange point 1, and Lagrange point 1 gives you a direct view of the sun. I'm not necessarily happy with just that, because it would be a lot better for our models if we had more three-dimensional stuff. And so at the very bottom there, you'll see that we have a satellite coming up in the early 2030s at Lagrange point 5. That'll help. That's the European Space Agency's Vigil satellite. But the other things I wanted to point out is that Michigan has now put up software that tells you where the aurora is and what it's doing in real time. And there's also a pretty important thing. There's beta release software from this guy, Sandeep Chittamali, and it's in alpha release now. It's been tested by a number of people. And so the purpose of that software is if you're out on a ship or you're in a field camp out on the ice, you look at that data set. It will tell you exactly what satellite is going over, where you are, and when. And so you can collect your field data and know exactly that you're underneath the satellite. And we really haven't had that before. So that's pretty useful. You can just email him at that email and he'll send you a copy of the stuff. It's free software. So looking at what the new sensor technologies are, I'm very involved in the eDNA sensor technology. The reason for this is it gives you biodiversity, seasonal habitat use. It also can monitor disease organisms and invasive species. And in the Arctic, we're getting a lot of invasive species in Alaska. So there is a Marine Technology Society eDNA group. There's a web page there. They have meetings about once every month or so. And there's a big microbial sampler shown on the right-hand side there from Woods Hole. And then there's also a sampler for eDNA for an AUV. So those are coming up. And then how can we couple observations with satellites and in situ? There's shown picture here of a stern-deployed moon pool from a Chinese vessel so that they can get their autonomous underwater in and out under the ice. There's a sort of interesting picture of a robot dog towing an EM ice thickness sensor. And then there's a University of Alaska Lacetos long-range airborne sensor that's carried by an autonomous aircraft. It combines a laser and the EM technologies that was mentioned earlier. And then there's a Portuguese EM gradiometer, which is used for tracking power cables. And so that's a combination of some things that we're getting to here. So with dual-use technologies, some of the sensors that we're really keen on are those that provide undersea navigation. So ELORAN, it's much stronger than GPS and it penetrates water to a fair depth. Geometric sensors are, there's a picture of them being deployed and recovered from an AUV there. They cost about $5,000 a piece. So far, they haven't been tested, but they should provide sensing to about a meter at 1,000 meters range depth. And then there are quantum magnetometers and gravimeters. These are now small enough to go on autonomous underwater vehicles and small unmanned aircraft. The trick is that you have to have a database recorded with the same accuracy. They're much more accurate than regular magnetometers and gravimeters. And you have to have a large language model to compare the data to get your information back in real time. There's a very nice comprehensive review from my friends at NATO CMRE. And the other thing about these quantum magnetometers and gravimeters, you can monitor or figure out exactly what the quantities are for your seafloor mineral deposits. And that data is not very well known right now. I'm on the working group for that in the US. And you can also detect hostile autonomous underwater vehicles. So in terms of transformations, what are we going to do in the future with unmanned systems? I think that's a key thing. There's 4 kinds of unmanned systems. We're talking about high-altitude pseudosatellites, unmanned aircraft systems, autonomous surface vessels, and autonomous underwater systems. There are HAPS that exist. They're solar-powered for the most part, and the ones that aren't solar-powered, none of them have been tested in the Arctic. That's something that experiments are planned for in the coming year. In terms of high-altitude, long-endurance aircraft, we've been trying to get these Predators, as I call them, up there. Canada has purchased 2 of them that they'll have underway in 2028. Norway also has some. The US has some, and we still haven't gotten them in the Arctic, but there are plans to do that, and that should provide us some of the persistent maritime domain awareness that we'd really like to have. Autonomous surface vessels don't really work all that well in the Arctic, over 10% ice cover, but they are being used in ice marginal areas, and NOAA has a big contract for that now. And the key thing is probably autonomous underwater vehicles, which come in different flavors, gliders with propellers, and then various sizes of autonomous underwater vehicles. And the key thing for those has already been described for gliders is buoy-based acoustic triangulation for their positions. What we really haven't done yet is a lot of swarm mapping for those to map oceanographic, hydrographic features and fronts. And so in terms of data transmission, and long-term interoperability. As most of you probably know, under ice acoustic data transmission is difficult because of melting water and stratification and sea ice roughness. I've been looking and working with optical modems, which have a much higher bandwidth. Their range is about 350 meters right now, but they have a very high bandwidth. And we could extend this by using gliders as data mules to get close enough to get the data transmitted. Dalhousie just had won the OES Ocean Challenge Award for magnetic induction for CTD's data through sea ice. I'll show a picture of that next. There's a reference there. And we've been using autonomous underwater vehicles to unmanned aircraft. And so we have done that through the sea surface at various wave states, and we're trying to get that done. We could possibly do it through sea ice. We have an upcoming conference in June on undersea quantum communication that would really go a long way to solving the problem. But one of the key things is under ice buoys that can harvest internal waves and currents and then transmit the data to autonomous underwater vehicles. And in terms of, I'll show a picture of that in the next slide, in terms of interoperability, NATO has got some standards, including for optical underwater communication, but we still need to work on those. This is just a picture of, I mentioned that magnetic induction communication through ice from Dalhousie. The picture on the lower left shows MBARI's AUV that harvests wave energy and surface energy and transmits it via niobium connector, and then the under ice Dolphin Labs technology is shown there as well. So the key conclusions here are for satellites, the NISAR stuff is what we are really looking forward to. For new sensors, I think I'm very excited about the eDNA capabilities that are being developed now. There's still a lot more work to be done with that. And in terms of remote sensing operations, I think that that's one of the key things is we haven't really gotten synthetic data at the exact same time that we're getting the satellite data, and that's really been a problem. And the priority for the synthetic aperture radar data is looking at the dynamics of polar lows. Many of you are aware of that. I'm looking at the quantum magnetometers and gravimeters for what we're seeing for security and for more research on the just general structure of information. I believe we can also get sea ice thickness from both of those sensors as well. So that's something that could be done from unmanned aircraft. And for unmanned systems, we really are going to try and use more of high altitude and long endurance aircraft and regular unmanned aircraft and autonomous underwater vehicles, especially those that are charged from subsurface energy harvesting systems. And in terms of data transmission, I really think we should try and work more on optical communication. I think we've kind of personally run out of advances in acoustic stuff. Not everyone agrees with that, but we could do a lot more. And then we're going to need some data standards as well. So I think that's pretty much what I had to say.
Thank you very much, Philip. Please put your questions in the app, and we'll take them at the end. Next speaker, please, is Håkon Sandven from Bjerknes Center and the University of Bergen. I'm going to shorten your title. You're looking at the lightscape in the Arctic.
Hello, hello. Thank you for the introduction. Then I don't have to spend much time on the first slide. So I'm a light person coming from the physics department in Bergen. So obviously I think light is super important, and I hope to convince you as well. So light is perhaps the physical variable in the Arctic that changes the most throughout the year. It varies by about a factor of 8 orders of magnitude, so a factor of 100 million over the course of a year. And it's important because it fuels the primary production of algae and phytoplankton in the water, but it also affects the lives of zooplankton and fish as they go up and down in the water column and try to eat but not be eaten themselves. So fundamentally it's a big part of the question of, okay, how will the Arctic Ocean look like in the future in terms of ecosystems? It's also super challenging to observe and model it. You know, if you lower a thermometer on the side of the ship, you get the temperature. But if you put a light sensor on the side of the ship, you get the shade of the ship. So it's a bit more trickier than many other parameters. It's not only the sun that drives the variability, you also have things like the moon, northern lights, you have clouds and sea ice that are super important for how much light is getting through into the ocean. But also you have the stuff in the water itself. So you have the phytoplankton and you have sediments from land that are a really important part of the equation. So it's quite fun thing to work with. So in marine optics, we are interested in not only finding out how much phytoplankton there is, how much zooplankton there is, but also how they're responding to climate change. So yeah, I've talked a bit already about this. It's really difficult to observe. Sensors are not really that good. It's hard to get the ecosystem responses correct. And on the modeling side, there's so many different parameters that go in. All of these have really big uncertainties. And we also don't have that many observational data sets. So I've been working a bit in the Barents Sea. That's the easiest thing you can do. The changes have been so massive in terms of sea ice that we see really big changes just looking at kind of before and after with the ice. So we see now that you can have 1 month-ish earlier phytoplankton bloom than in the past. But then as we move up to the central Arctic, it gets a lot more complex and yeah, fun. So here you have lots of fresh water that comes in from Siberia into the central Arctic, which has kind of this tea color with organic matter that colors the water and also makes the light attenuate a lot faster than in the Barents Sea. So this can reduce light availability by around 60% at 40 meters, and by that postpone phytoplankton growth by a few weeks. So it divides the Arctic Ocean in two, in the European side, but we only have observations from the summer, so when the ship is up there, so we lack these seasonal observations. So what we do in most of the world ocean where we want to look at seasonality, that is to use satellite observations. But this is super tough to do in the Arctic because these are ocean color satellites. So with those we get nice pictures of the ice, but nothing about what is underneath. And there's also a lot of cloud cover up there that makes it tough. Ice-tethered profilers is the most mainstream option now maybe. Here you get real-time data. It is stuck to a flow. So you get very nice data of that exact flow. But the trouble with that is that you don't catch all of the variability that is going on the larger scale. So if you have a lead that is 200 meters away, you miss that lead for the whole duration of your deployment. So we can get really nice data. We have tested it a little bit on the cruise last year. But I think the best solution would be to get these type of sensors on moorings. So here you have one fixed location. It looks upwards, and you get the variability as the ice opens and closes. So you get a very nice large-scale image. But optical sensors don't capture what is going on in the water column. We don't get the phytoplankton spring blooms that pops up in early May. We don't see them. So that is a bit of an issue that we need to work on. So to summarize, the Arctic is really rapidly changing, also in terms of the lightscape. This is affecting marine ecosystems on all levels. Both sea ice and runoff from land are important factors that determine what light conditions you get. And we will likely get a very regionalized lightscape with the transpolar drift and the Nansen Basin, even after the ice is gone. And we really need to have more of these year-round measurements that we are currently missing. Yes, so thank you for your attention.
Thank you very much, Håkon. Do we have any questions?
So, are you interested in bioluminescence as well?
I've seen some really nice talks, and I've also seen some weird data. So I am interested in it, but it is quite difficult. It's even one step up, I feel, in terms of the underwater light. But I agree that it plays a probably big role. So it will be interesting to see data.
Any more questions? I have a question. Of the presentations this morning and in this session, which one would you like to work with more closely?
It's tough. No, I think with the NTNU guys and the satellite that I have, there is a really lot of strong synergies, and be able to see where you have cloud cover or not on this photo. Yeah. Being able to see, okay, here you have an opening in the ice, that would be pretty cool.
Good. Thank you.
Thank you.
Thank you very much, Håkon. So, as I work for an energy company, I have a safety statement. A known situation is a prepared situation. And what we've been presenting so far is data collection. But why? Why do we need the data? We need data to make good decisions. And the next presentation is one of the toughest questions, I think, in the Arctic, and very topical at the moment. So it's my pleasure to welcome Professor Karin Buchmann from the Copenhagen Business School. She's a professor in, I think, Arctic Sustainable Resources. Is that correct?
Well, I lead the EU Arctic thematic network on Arctic sustainable resources and social responsibility. So actually my field is more the field of business and human rights, which is the one I use as an angle for this presentation and research on deep sea mining.
The floor is yours.
Thank you. And there is a presentation. Is there also a clicker up here?
It's the one on the... It's on the table.
Oh, this is a clicker. Okay. Okay. I think it was just there, but I don't think I touched anything. Am I supposed to open it here?
I think.
No. Okay. Here we go. At least we go down there. We need to put it up there.
Yes.
There we go. Okay. Thank you very much. So what I want to share with you now, we've been sort of at the top of the ocean and a little bit into the ocean. I'm going to take you to the bottom of the ocean, the real bottom, like 4,000 to 8,000 meters depth. And I'm going to give you a little bit of a social science approach to the natural science and interdisciplinary aspect of deep sea mining. So what I'd like to share with you, and of course 10 minutes is very little to do something that is as complex as this. A little bit of deep sea mining, what it is and how it's done, and what are the issues in regard to potential impacts. Walking us through a little bit the impacts of potential...
You need this one.
Yeah, it's just because the light really gets into my... Thank you, thank you, thank you. A little bit on the economic arguments and environmental sustainability impacts for why deep sea mining could be a good idea. Then move on to the uncertainties. And then based on the uncertainties moving on into some of these basic issues I really want to propose, which is why the risk, the lack of knowledge that we have on what the impact of deep sea mining could be in the ocean calls for a risk-based approach that might even go beyond the conventional precautionary approach that we have under the international law of the sea. So first of all, of course, this is based on a 5-year research project that I'm about 2 years into with my team. When I applied for this, I thought we were going to look at the the Pacific Ocean, sort of the Clarion-Clipperton zone of Hawaii, and maybe also the Papua New Guinea. What happened in the meantime, a week after I got my grant, Norway announced their policy to start deep sea mining. And even though that's been paused then about almost a year ago now, US President Trump also announced that the US was going to go into deep sea mining. So in some ways we've been sort of overtaken on the inside, and it's certainly a moving target that we're working with. A little bit of what is this deep sea mining? So some of you might be familiar with it, but maybe someone else. So basically we are talking about 3 types of sort of collections of minerals that are basically critical minerals. So some of these critical minerals like manganese and other minerals that are needed for a number of purposes. When I started working with this, the big argument was this is something we need for the technical solutions for renewable energy production, for example, for the magnets that we need for energy production in windmills or in hydropower plants or for power storage and batteries. In the meantime, of course, the geopolitical situation has meant that now there is another big emerging market, which is the so-called defense industry, which I might want to call something else, but anyway, that's the official term. And so where do we have these minerals? So basically where they collect, and they're in 3 forms, right? But basically where they collect are sort of around these the tectonic plates. So they're like so many other minerals. It's basically based on magma that then comes up to the bottom of the ocean, and they solidify. And that's why we can see there are 3 different forms and 3 different areas, but all the nice little red dots there around the tectonic plates. And you will also see that that's also where Norway is looking, for example, at some of those very close to the east coast of Greenland, due to the fact that Norway has a very big sea space based on islands in the North Atlantic. So what are some of these arguments driving this? And this is probably a slide or information that some of you might have seen before. Is from 2021 from the International Energy Agency. I've seen people with more expertise in energy production and critical minerals use this also just a few months ago. So this is still valid. And basically, what I want to share here is just to get you to think about and to sort of recognize the extreme difference in minerals needed for renewable energy production and storage as compared to conventional energy production and storage. And there are a number of different minerals. Of course, copper is really, really big, but there are also some of these more complex and rare earth minerals. So without going into too much details on this, there are also a number of challenges around this. For example, we know that there are, in terms of environmental and social impacts for the mining on land, there are a number of impacts that have led to complaints, that have led to damage, and that is also challenging the corporate license to operate of the industry, and also being a problem for governments that want to support this, for investors, etc. So this has been sort of driving this argument that this slide shows, by the way, some of the social impacts. There is, except for North America, most of the social impacts are affecting people who already live in relatively precarious situations. This might also happen in North America. Basically, people who live in rural areas, or indigenous peoples, or both. An important point is actually these are not just impacts affecting indigenous peoples. This is something I often hear, isn't this just about indigenous peoples? But it's about so many different peoples, not just indigenous ones, also ordinary non-indigenous ones that might not even have the additional protection that indigenous peoples have, at least in some countries. And so this has sort of been driving this argument that, hey, when there are so many problems with land-based mining, why don't we just go and pick up these minerals? There's some of them are just sort of lying in these so-called potato-sized chunks at the bottom of the ocean, right? So in some ways it might be a really, really nice argument. We can have a green transition or an energy transition that is sustainable also and not creating havoc on land. So that's the overall argument. Of course, it's a little bit more complicated because there are also economic aspects around this. But the big question, and that's where we get to what we don't know, that's the ecosystemic impacts. Because we're talking about something that happens at the very bottom of the ocean. We're talking about something that happens at a part of our globe that we know less about than we we actually know about the moon. And we're talking about something that happened. We're talking about something that's not just an empty glass, just a glass of water with nothing else, right? The ocean is a very, very rich ecosystem in itself. It's also an extremely fine-tuned ecosystem. If we look at these processes, it's different life forms that exist under very high pressure, very completely dark. And also very fine-tuned to sort of regeneration in an area where there is little disturbance. So what will happen if we get to these processes whether it's sort of with the existing techniques, and there are people experimenting on making sort of less disturbing techniques, but I think as most of us know when we go and dip our toes in the water in the summer, that there is sediment arising. So in this case, when we do deep sea mining, there's also likely to be sediment arising, even though there's some new scholarship saying maybe sediment is not such a big problem, but it's still going to be released, either at the bottom or in the process of sort of doing preliminary rinsing of the minerals at the top. Right? So at the end of the day, what we really don't know yet is what are these implications, not just for the fish and sea mammals that live in the ocean, and also maybe some of the talk has been about sort of island communities that might be affected, maybe actually not such a big problem because much of this mining will be far from island communities. But the bigger question is, what's it going to do for the overall ecosystem? Again, also recognizing that we don't know a lot about the interaction between the sea-based ecosystem and the land-based ecosystem, right? Might we in fact have a repetition of this nice picture that we've seen for the energy transition on land? We've seen lots of the SDGs going down the drain and the hole in the effort of addressing climate change. Might we have the same, basically, in the ocean? So this takes us to this idea of a human rights impact assessment and human rights due diligence. Why is that? That's because if we end up disrupting the ecosystem in the sea, and it might affect the ecosystem on land, and that's what we really don't know. It will affect also all sorts of human rights of individuals, and we have a really detailed set of regulatory framework here, a lot of standards that countries have committed to, and we also have really, really nice, although it be soft law guidance, but also some hard law rules. And the point about this is a risk-based due diligence process, which is an ongoing process in which companies identify and address the risk that they might cause to society, not just here and now, but in a long-term process. And so the argument I'm trying to make, and I'm going to wind this up because time is running, the argument that we want to make here is that we don't actually need to reinvent anything here, because we have these human rights standards that countries have already committed to, that already apply to all companies anywhere in the world, and they already provide really, really good guidance. So the point is here, this is not just for companies, investors, the mining industry, it's actually also for governments to live up to their human rights obligations and say, if there is a risk that is so big that we might end up creating more havoc for the globe because we don't know about the risks. This is such a big issue that it needs to be considered for any sort of deep sea mining to be advanced in a way that is responsible for in the long term for the globe. And it also means that investors, the industry, innovators, whatever, should really think very, very carefully about the risk that they might cause because we don't have knowledge. And also, of course, this also feeds into what are some of the vested interests that, for example, the industry has when, for environmental or other risk assessment purposes, the knowledge generation is typically delegated to them, which is conventional also under environmental and other types of impact assessments. But there we usually have already established knowledge to hold them to account for. So thank you very much, and apologies for really mixing up things, but it is very complex.
Thank you very much, Karen. You know where the app is for questions. So, next speaker, please, is Sasu Katiamaki. Close enough. Yes. From the Finnish National Defence University. I know what this is going to be. This is yet another interesting topic, shall we say, on Chinese scientific Arctic expedition activity. Sasu, the floor is yours.
Thank you. Hello, everyone. My name is Sasu Katamäki. I work at the Finnish National Defense University. I work in a project called the Arctic Axis, which looks at China's and Russia's activities in the Arctic and assesses the security impacts for the Nordic states. In this presentation, I will be briefly talking about China's Arctic expeditions, the kind of the long history and their polar AUV programs, in an effort to evaluate the progress and the backgrounds and the kind of the research motives. So here is a picture from this year's expedition. The Jialong manned submersible was used during the expedition to do some under ice exploration, but I'm going to be talking more about the AUVs, which are, as you heard in the earlier presentations, they're a kind of type of autonomous underwater vehicles or a subtype of underwater vehicles that are used to complete pre-programmed tasks, and they have significant dual-use purposes because they can carry a lot of different kind of sensors and they can complete some activities, both research and activities for research and military purposes. But in polar research, they have been mostly used for under-ice observations and oceanographic research and other distinct uses such as this. If we span out to the kind of the long history of Chinese research activities, or the short one, if you want to call it that, but these expeditions started in 1999, and China has conducted 15 Arctic expeditions since then. I went through the mission reports for my PhD research and other Chinese language sources, and from these statements we can see that China has tested 8 different types of AUVs, with 7 or 6 of them being classified as some type of AUVs. And what is really interesting for my part, because I'm looking at military civil activities and dual use in my PhD, is really the kind of the how these programs have been integrally linked to China's military and civil high technology programs from very early onset. So I have been able to kind of link all of these programs to different national programs that they have for developing. So this development of polar AUVs has been really one subset of this marine robotic development in China, and this kind of the history has been that during this, between 2003 and 2025, there have been 8 different kind of devices tested. So I would myself, I have compiled a graph here of the different tests and devices. I don't have much time to go into great detail about these, but I would separate these into 3 distinct periods. So between 2003 and 2014, we see kind of the early period of these tests. So for example, China built this prototype of ROV, which is a remote operated vehicle, which was used for to deploy from open waters and look at the near ice and a little bit under the ice from a workboat. And then they, through these successes, they built their first prototype, which was the Arctic ROV, or the Beiji ROV, which was deployed to ice holes to look at the under ice for under ice observations. Then, from what we can see, how it progressed after this is that there came a period between, let's say, 2014, 2020, where they tested a lot of different kind of devices, and look at their applicability for the polar research. So they tested these different kinds of AUV gliders, and then their operations in open sea areas, so in the Bering Sea and the Druk Sea. And they kind of, these devices were not built for the polar activities, but they were as part of national tests, actually tested in the Arctic to see how they fare in the cold conditions. Between 2021 and 2025, we see kind of the expansion of these activities to under ice and polar or to deep sea areas. So, and this was really spurred on by China's national research and development program, which specifically kind of focused on applying these and developing devices for both polar and deep sea activities. So we see this with the Tansuo 4500 and then more from 2023 onwards, more specifically more kind of more advanced and sophisticated devices. So if we look at the kind of the broad span of things we see in terms of scientific research, they have gone from like open water deployments to ice hole deployments, then to testing long-term observations to AVV gliders, and then to under ice and deep sea exploration in the past few years. Behind these, and which is for me, it's the interesting part, is really two institutions. So there's the Shenyang Institution of Automation, which has been called the kind of the cradle of China's robotics. It was responsible for almost all of the devices until 2021. And then the second one, which is more interesting and really demonstrates kind of the military-civil fusion strategies of China and how these feature together the civil and military, is the Harbin Engineering University, which also houses so it has been responsible for the devices after 2023 and notably it also houses the kind of the military AUV programs and the intelligent marine technology programs and the polar acoustic laboratories. So I would, and it's very integrally linked to the national defense sector. So these two institutions are really behind these programs. When I was thinking, when I was going through these mission reports and trying to figure out, so what is the kind of the capabilities of China have? Currently, so they are behind Western counterparts. So we are seeing now them to kind of expand to areas very rapidly, which was already tested in different Western countries 20 years ago. But the development has been kind of fast, and it's spurred on by these national initiatives. If we just look at the mission reports, what is able to be discerned from those, it very clearly points that these are used for legitimate scientific research. But then if you assess the kind of the dual use, you have to really look at the kind of the deployment patterns and how these are developed, what are behind the development and the technical characteristics of these devices. So those point to more towards this, that it's integrally dual-use development. And in the past few years, we have seen this growing trend where these close links between the military and the civil in these AUV development programs, which have been there from the onset, have grown stronger. And then we see this kind of that the focus is really on kind of combining this deep sea and the antipolar exploration, which in the kind of the Chinese sense are these new strategic frontiers, which China needs to develop technologies towards. So I think I'm gonna end here, but look forward to your questions and thank you very much.
Thank you very much, Sasu. Are there any questions? I have a question.
Yes.
It's always good to have a question. Do you think the Chinese are ahead of Europe today?
No.
Will Europe keep ahead of China?
I think it's going to be debatable in 10 years. So I think we will have to see. Currently, they're catching up, or kind of the capabilities of what we have had for quite a long time. But then these research programs are really spurring on the development in a fast. And even though it's not a priority, they're putting still substantial monies and towards these projects. So
So in the future, it'll probably be more like-for-like development.
Yes, yes, and we see this also in polar research in other areas, that it's in terms of like published papers and the applications of these devices, that it's starting to be, they're catching up.
You have 10 seconds.
Thank you. I'd be quite interested to know how you monitor this. Is this through publicly available data that you get from the Chinese sort of authorities, or is it also sort of other forms of data?
It's a lot of these kind of mission reports that the Chinese scientists have written. So and actually they have published quite a lot in their state medias about this. So it really shows that these are kind of like state endeavors and national achievements when they test something new. So from these I have been able to gather like most of the data. So thank you.
Round of applause. Thank you very much. So next it is Roger Birkeland from NTNU, the Trondheim Technical University here in Norway, on a more neutral topic. Back to neutral water, shall we say.
Yes, something like that, maybe. Yeah, my name is Roger Birkeland, and I will talk about, let's say, more of our visions for how this observational pyramid can grow in the future, including for the Arctic areas. So we have seen today a lot of the different, let's call it, parts of the observational pyramid already. So I will not talk about more of the technical details. There has been a lot of presentations about in the ocean and also the remote sensing part, but I'll try to put it into some bigger context also. But I wanted to put one of the pictures from one of our satellites, the Hypso-2, from the area around Longyearbyen last summer, just to show what we can do with a relatively simple university satellite also. But the idea here is to try to show the context around us. So since the 70s, we've had Moore's law to predict the increase of computational power, and that can almost be a proxy for technology advancements in itself. So now this is accelerating in all domains. So technological breakthroughs in one field can enable advancement in other fields. But that means that we then need to be fast to keep the pace. So hopefully we can use what is going on to enable to collect more data to a lower cost, and in a way so it can pave the way for new exports and new industries. So now it's about 3 years since the release of GPT-4, which almost turned the world upside down in a day. So the 2-year cycle for Moore's law is now maybe approaching 7 months for AI systems. So the capacity is increasing a lot, but it is even more difficult to measure the development. The impact for us and the society is probably still unknown, but we need to at least try to be in a position to understand and use the impact. So how can, for example, the AI systems be used to, or not used, to gather more information and fusion of information, and in the end synthesis of knowledge for in situ and also remote sensing data. Another aspect in this is how policies also change and adapt. There was a recent report last year that the Norwegian government determined that we will have one common system for research in Norway, covering the open research, but also the more protected research. And the reason for this is that civilian and commercial research develop in a pace where it's hard to keep up. So we need a broader collaboration across open and more closed domains. So there has been some mentioning of dual use research in this session, and I think that there will be a need for more of that. And probably also at universities that haven't had that as a tradition yet. But with the different situations we now have, the civilian sector need to contribute more to the total preparedness. And then we can also mention the change in the technological center of gravity. Several reports have shown that China now is taking over as the leading actor in many different technology domains. And most likely this will also be enhanced further, as we just heard in the previous talk. This might bring us some dilemmas, because China will be the leading nation in many areas, but within several of those fields we are maybe not to collaborate due to the security issues, or also fear of infringement of technical and personal and security related information. So then the question to us will be, how can we position ourselves and keep up? So we need to more or less strengthen what we are doing. We know that Norway has a large exclusive economical zone that we need to monitor and protect. This area is extremely rich in resources, food, biology. Also we heard about geological resource, both known and unknown. It is an area of a lot of traffic and also tourism. So what we need is to build better infrastructures and more infrastructure to monitor what is happening here, and probably also on a layer of sharing the data between in situ and all the nice buoys and tethered solutions we have seen together with satellites and other parts of remote sensing. So this will bring on opportunities, I think, and the Arctic is getting a lot of focus through the polar year in a few years, and also the Arctic Ocean 2050 program that will start soon. So in this we should hope for increased investments in research and education, so that we can build more infrastructure. We need more autonomy, robotics and surveillance. And also I think the dual use will become a factor here. The Norwegian government has released an ambition of a full value chain for space industry, for example, but that also means that we need to strengthen education and research on these topics. So to wrap up a little bit on what we are doing at NTNU, across several different domains, like I mentioned, AI, autonomy and remote sensing, we need to work through better and several research projects and collaborations to advance the technology. And we need to adapt the educational programs also. We are doing that because we need more people both to collect the data and also to analyze the data that we have collected. And this calls for, of course, collaborations between different fields of research and also different locations. There are initiatives that can cover different locations from different research organizations, but we need to find more ways to collaborate together. So hopefully, both the global politics and the Arctic will cool off in some time, but we maybe need to accept that it will not, and we need to be prepared to work together to build robust research platforms and systems if it will not. So I think that was what I wanted to say, so thank you for your attention.
Thank you very much, Roger. Are there any questions? You know where the app is. I encourage you to use it. Then thank you very much. And then we go to our last but not least presentation from Kim Young-hun. He didn't actually say which university you're from, so you can introduce yourself. The floor is yours, Kim.
Okay. Good afternoon. This is Jang-yeon Kim, and I'm a PhD student from the Korea Polar Research Institute, and I'm from South Korea. And today I would like to talk about more science results, and it's about the specific distribution of zooplankton in the Western Arctic Ocean using in situ imaging approach. Traditionally, zooplankton research has largely relied on net-based sampling. But however, recently, imaging-based instruments like this, the underwater vision profiler, UVP, have received increasing attention because it provides cost-effective and depth-reserved observation and new insights into the functional role of zooplankton. And my study area, Western Arctic Ocean, is undergoing the rapid environmental change. The sea ice is declining, and the Atlantic origin water is increasingly affecting this area. It is Atlantification. However, under these changing conditions, there is limited understanding of vertical distribution of zooplankton and its ecological implications. And at COPRI, my institute, we going expedition every summer to discover this kind of response in the ecosystem. So my objectives are first, to characterize the vertical distribution of zooplankton using in situ imaging approach. And second is to identify environmental drivers of the vertical distribution of zooplankton. This is my research stations. During August 2023, during midnight sun, I operated this UVP and mounting on the CTD Roger profiler. And UVP can capture over 600 micrometer size zooplankton image. So, and also I classified a lot of images in ecotexture application, and I converted it to the abundance. And UVP can provide not only the zooplankton image, but also particle measurement data. So I analyzed the particle concentration and biovolume. And I analyzed CTD-derived the environmental parameters. So using environmental data, I analyzed the clustering, and my study area divided into 3 regions. The one is the East Siberian Sea, ESS region, and Northern Chukchi Sea, NCS region, and transition zone between them. now is for the hydrography from the ESS toward the NCS. There was these red lines indicates Atlantic and Pacific origin water boundaries, and it showed the boundary is progressively deepened toward the NCS. And below these red lines indicates there was the Atlantic origin water, and above these red lines there was the Pacific origin water. So it suggests the Atlantic origin water it showed steadily flow from the ESS toward the NCS. And also there was no episodic physical events. At that time, in the TG region, there was the thick layer of nutrient-rich Pacific winter water. And then in the euphotic layer of the TG region, there was high chlorophyll A and particle concentration and biovolume. And interestingly, this biovolume per particle it means the particle size, and particle size remained high even at deeper layers. And this is hydrography. And now is for the vertical distribution from the in-situ imaging approach. UVP captured mainly Copepoch, Ostracoch, and Lijaria, and they showed widespread occurrence. Lijaria, this zooplankton group, is usually it's not easy to capture using the zooplankton net. There was a different result compared to the net sampling. And the Eumalacostraca jellyfish and Limacinidae, they showed localized occurrence. And Appendicularia and Chytogonus and Annelida, they occurred sporadically. And to simplify the results, I analyzed the region average distribution. And as I expected, Copepoch was highly dominant in this area. So at first, I checked the distribution excluding Copepoch, and I saw the second dominant species was Ostracoch, and their distribution was their vertical distribution was associated with Atlantic origin waters. It followed their distribution was gradually deepened toward the NCS region. And Lijaria, their distribution was Pacific summer water in the NCS. And after that, I checked the Copepoch, but UVP is difficult to identify the Copepoch species because of their low resolution. So I analyzed the morphological traits based on image data according to the previous paper. And the size and transparency was has the high explanatory power. So the Copepoch were categorized into 4 types. So I can see like this, the vertical distribution of Copepoch type. So in upper layers, there was larger Copepoch. The larger Copepoch were more observed in the upper layers. And in lower layers, smaller Copepoch were observed more. And interestingly, in the TG region, zooplankton abundance consistently remained high between these water depths. But the chlorophyll and particle concentrations was concentrated in the really surface layer. So this abundance, high abundance, might be related to the particle size. So it suggests the greater importance of particle size for opportunistic mesopelagic Copepoch. And also, when it comes to the transparent, this in the TG, the opaque copepoche was increasing with depth, and it supports the better food condition because the transparency can be decreases because of the better food quality and food availability. So to summarize, our UVP data revealed the distinct vertical distribution of zooplankton, and the second, Ostracoda and Ligeria, especially these two zooplankton group, was associated with the water mass properties. And copepoche exhibited the depth-dependent distribution based on morphological traits, and the mesopelagic zooplankton abundance was more linked to the particle size. Thank you for your attention. Yeah.
Thank you very much. Yeah, thank you. Are there any questions, or do you all want to have lunch? My first thought is that I think the research you're presenting on the Atlantic water impact and the work that's presented about the Siberian water runoff, doing some comparison work there, I think has some. I think there are opportunities there. Thank you very much.
Yeah, thank you very much.
We have had one question on China, China security. Regarding China's undersea research, what type of additional testing do you expect to see this summer? What are the country's key gaps in advancing its polar program?
That's actually a good question. I think the areas where I expect most research, or that they're trying to test the most, is this acoustic navigation and communication, and then also how to better link up these devices to maintain connection with these AUVs under ice. So far the tests have been relatively limited, but this summer they demonstrated really that they're able to go to up to, for example, 3,800 meters below the sea ice. So I expect maybe that they will continue to test these areas, and then maybe go to the most depth area, or the kind in the Arctic Ocean at some point, to test how really it works here. But I think there's a lot of small things that they're trying to navigate now in this regard. Yeah, thank you.
Thank you. And thank you to the audience. Thank you to the speakers. I hope you've enjoyed this session. Back in the 90s, I read Tom Clancy a lot. There's a lot of well-researched books, but it was all fiction. Today, that fiction is becoming more fact. Enjoy your lunch.